Thank you very much. It's a pleasure to have you here. I met some of you already last night, but for those of you that arrived just today, my name is Antonio Faraone. I am one of the instrument scientists for the neutron spin echo spectrometer here. I think one of the most interesting part of this workshop would be the breakout session. And in particular, together with Professor Tadanori Koga from Stony Brook University, who will arrive around lunchtime, I will be leading the polymer group section. I think probably the majority of you work with polymers. Can you raise your hands if you work with polymer? Oh, everyone. So I wasted half of my slides, but for those few that are not familiar with polymers, I just introduce what polymers are macromolecules formed by a large number of equal repeating units that we call monomers. And of course, when I say a large number, is ranges from hundreds to even millions of these repeating units. And because of this particular structure, actually, many of their properties are actually related just to their lengths and the fact that they are so long. Nowadays, however, this very simple structure is, of course, is still applicable, but there are other progresses, and synthetic chemists can do much more than just repeating units of the same. They can do copolymers, where they mix different units, monomers. They can do different architectures like stars, or even more fancy things like comb, copolymer, bottle brush, and things like that. However, of course, also polymers exist in nature, and we have many relevant nature-made polymers, in particular, for example, DNA and collagen and other things. As far as synthetic polymers, they are used everywhere. They make rubber, plastics. Together with, if you add nanoparticles, you can make light materials, like in airplanes. They are used in the field of energy conversion and as a stimuli responsive system. So polymers are everywhere and still very important in a field of active research. What I want to draw your attention to relate to the workshop is because of this chain-like nature of polymers, we have a hierarchy of structural and dynamical process. From the very atomic length scale dynamics of the maybe the rotation of a methyl group, then we go up to the segmental relaxation, the alpha relaxation, the dynamics of a chain, one with respect to the others, and then dynamic processes that actually are determined by the chain nature of the system, like arouse and reptation dynamics. The reptation is the snake-like motion of a polymer and within the entanglements created by the other polymers, up to the large-scale center of mass diffusion. And all of these dynamics take place in the system, and they are activated usually at different temperature range and determine the properties of the systems. So in particular, in the neutron spin echo breakout session, we are going to focus on and show how spin echo can probe, in particular, this range of time scale and length scales, essentially what is the arouse dynamics, the segmental motion of the chain, as well as effects that are related to the entanglements of the chain with each other, so related to the reptation motion. So that's what we are going to focus. But of course, there are other neutron scattering techniques that can probe other dynamic processes, as well as many other experimental techniques that you can use to characterize your system. And now, I think the next 3 slides are the only reason I put them there is to whet your appetite for doing spin echo with your own things, just showing what has been done as an example of using spin echo to investigate this system. So I have 3 cases. One is about nanocomposites. There is an effect that is somewhat interesting. So if you add nanoparticles to a polymer melt, what would you expect? To the viscosity to increase or decrease? you have a 50% chance to get it right. And actually, I will tell you, it's a 100% chance to get it right. So
Neither.
neither.
All of you.
Both. Let's get the both. So usually the obvious answer would be that the viscosity will increase. That's what the basic model, Einstein model will predict. However, there are reports that in some cases you can add nanoparticles and obtain a fluidification effect. And so in one of these studies dated by 2017, Dr. Senses, now Professor Senses, investigated the effect of different sizes of nanoparticles in a polymer melt. And using spin echo has shown that adding small nanoparticles that are smaller than the entanglement mesh size, you obtain a dilation of the rectation tube. And that would explain the reduction in viscosity that you observe in certain cases. So that's just an example of how you can use spin echo to obtain information at the nanoscopic scale that would be otherwise very difficult to obtain. This is actually another example from the work of Professor Koga, and together also with Michi Nagao, that will talk after me. Is the other instrument scientist for spin echo. And this, I think, is again about polymer nanocomposites, in particular related to tire industry. So this is carbon black dispersed in polymers. And I think that to me, what really interests me about this work is not so much the application, but the fact that they have been able, using spin echo methods, to investigate the layer of polymers chains that are at the interface between the nanoparticles, the carbon black, and the polymer matrix. That's very difficult to obtain this kind of information, but fundamental to understand how polymers in thin films at the interface work and how this affects the overall dynamics of the properties of the system. And they, of course, have obtained experimental information about the slowing down of the dynamics of the polymer chain at the interface. And then, as a last example, I want to just show that similar, it's not just polymer nanocomposites. There are also energy polymer system in the energy field. This is a work done by the group of Professor Bassara. Whitney Liu was a student at the time. Now she's a professor at the University of Wisconsin. And she's interested in making basically solid-state electrolytes for battery research. That would be a significant improvement in safety to the electrolytes we use nowadays that are flammable and liquids. And in particular, the system they investigate is a block of polymer, polystyrene and polyethylene oxide. And this block of polymer forms cylindrical aggregates arranged in hexagonal geometry. The cylinders are made by the polystyrene that gives the support, the rheological support, to make it solid. Instead, the red part here is the PO that is able to dissolve the lithium. And what they were interested in was the dynamics of the polyethylene oxide part, and to see how the lithium affects this. They obtain how the presence of lithium affects the polymer dynamics. And they will obtain more than one results, but in particular, I want to highlight how the spin echo measure were able to show how the presence of lithium ion affects the entanglement of the chain with itself, and therefore their dynamics. And that was particularly important when we use the batteries, when there is a gradient in concentration of the ions in the system. So I hope this just can start spurring your own interest, your own ideas about the system. And I just to, there is one slide left. I think I added it too late to be incorporated here, but never mind. It's just I wanted to conclude. Keep in mind the reason spin echo is powerful is, of course, all the great things that neutron scattering does that will be introduced soon, like isotopic sensitivity to light atoms, but specific for spin echo is the length scale and time scale that we probe. We will repeat this over and over again today, so even if I missed one slide, I'm sure you will see that again. And thank you very much, and I'm looking forward to working with you soon.